Hello friend, in today's lectures we are going to discuss about the stress distribution diagram for symmetrical sections as well as unsymmetrical sections for simply supported beam and cantilever beam. Let's see this. Here this is the symmetrical rectangular section, symmetrical I section, C section, U section, circular section, and in this way here stress distribution diagram is shown for the simply supported beam. In the simply supported beam, when the load act on it, its deflections take place in this manner. So at the inside section compressive stresses are induced, whereas at outer section tensile stresses are induced about this neutral axis. So in that case this is the neutral axis we have shown here, and compressive stresses are acting above the neutral axis. That's why this distance we may say this is YC, whereas tensile stress is acting below the neutral layer. That's why here we have shown that stress distribution diagram here, and that distance we say that is the YT. YT and YC means the distance from neutral axis up to the outer fiber of that sections. In this symmetrical section, sigma C is always sigma T. In this it means compressive stress and tensile stress should be same. Similarly, YC is equal to YT for the symmetrical sections, whereas in second figure it is shown unsymmetrical section, unsymmetrical I section, T sections, T section, L section. In that case sigma C is already acting in the upper side, whereas tensile stress is acting at the below side. But in this case sigma C never is equal to sigma T. It means compressive stress never equal to the tensile stress. Similarly, distance of this YC and YT never equal to. Is this right? So in that case YC never equal to YT. Now next, this for unsymmetrical section for simply supported beam. First figure is symmetrical section for the simply supported beam. Instead of that, if we say here instead of simply supported beam, if we consider the cantilever beam, stress distribution diagram will change, and in that stress distribution diagram for the cantilever beam, if we say this structure, the beam deflects in this manner, so it is in hogging. So tensile stress induced at the outer side, whereas this compressive stress induced is the inner side in that side. That's why at the neutral axis tensile stress induced at the above the neutral axis, whereas compressive stress induced below the neutral axis. That's why according to this, sigma T means tensile stress. Here we have shown here from above the neutral axis, compressive stress shown here below the neutral axis at an distance YC and YT. It is for symmetrical section. That's why we have seen here sigma C is equal to sigma T. Compressive stresses is equal to tensile stress, and distance of YC is equal to YT. That's for symmetrical sections for cantilever beam. When you consider here unsymmetrical section, in that case tensile stress is above the neutral axis as well as compressive stress is below the neutral axis, but sigma C means compressive stress never is equal to tensile stress, and distance YC never is equal to YT. Remember this point. Let's see the numerical. In this numerical, it is a cantilever beam is given which span is 2 meter and its cross section area is given 60 mm by 100 mm side, and it carries a 3000 Newton per meter load. So maximum bending moment when it is a cantilever beam, so in that case maximum bending moment at its fixed end, and that standard equation we have seen W L square by 2. So W is rate is given 3000 Newton into it is given 2 meter, so 2 bracket square divided by 2, so this become 6000 Newton meter. Now we are going to convert into Newton mm. So 6 into 10 raised to 6 Newton mm. Now y means distance of outer fiber from the neutral axis. So this distance is, we may say, y. So that total depth is 100 mm. So y is equal to, you may put here d by 2. Total diameter depth is 100 by 2. So that becomes 50 mm. I, moment of inertia for the rectangular section, is equal to 1 by 12 BD cube. Width of that section is given 60. Depth is given 100 cube divided by 12. So moment of inertia about the neutral axis, it becomes 5 into 10 raised to 6 mm raised to 4. Mm raised to 4. Now we have to calculate its maximum stress and its locations. So what is our flexure formula? Flexure formula says that m upon I is equal to sigma upon y, whereas m is the bending moment, I is the moment of inertia, sigma is the bending stress or flexure stress, and y is the distance from neutral axis to outer fiber. So m we know 6 into 10 raised to 6. I we already calculated 5 into 10 raised to 6. Now sigma we have to calculate, and y is the 50 mm. So in that case we will get here sigma is equal to 60 Newton per mm square stress induced at the outer section, means sigma t is equal to 60. So as well as sigma c is also 60 because it is a symmetrical sections. So that is sigma c, and outer distance y we already calculated, y is equal to here, that is 50 mm. So the maximum stress induced in the section is 60 Newton per mm square, and which is acts at the outer fiber of the sections. Now in this case again we have to calculate the stress at a fiber 20 mm from the top of the beam. Top of the beam means from that side. From that side we have to calculate the stress at this section, which is 20 mm from the top end. So in that case, if I say here this dimension is 20, so from the neutral axis I say that y1 is equal to 30 mm. 30 plus 20, that becomes 50, and we have to calculate the stress at this point. So we may say that is sigma 1. We have to calculate this stress sigma 1. This stress we may calculate in both types. In first types you may simply write the equation m upon I is equal to sigma 1 upon y. So m means, m we already calculated, 6 into 10 raised to 6, I 5 into 10 raised to 6, sigma 1 is unknown, and y1 is equal to, here we have to take y1 is equal to 30 mm. Therefore sigma 1 is equal to, you will get answer 36 Newton per mm square. This is the one way. Or in another methods you may say, consider here similar triangles. For that sigma is equal to 60 and its head distance is 50 mm. So you may say sigma upon y is equal to sigma 1 upon y1 according to the similar triangles. So sigma is equal to 60, y we already calculated 50, sigma 1 is unknown, and y1 is equal to 30. Again you will get here sigma 1 is equal to 36 Newton per mm square. You may use any method as per your convenience. Okay. Let us see this second numerical. In this numerical, length of the pipe is given 12 meter, inside diameter 500 mm, and thickness is 25 mm. So inner diameter becomes 500, outer diameters 550 mm, 500 plus 25, this thickness 25, and it is given supported at its end. It means it is a simply supported beam case. and density of metal and density of water is given. So in this case, first we have to calculate the weight of water and weight of the metal. So then we can calculate the total weight of that pipe with a full of water. Okay, now let's see. Length of the pipe is given 12 meter. Diameter, inner diameter is given 500 mm, and outer diameter of the pipe is 500 plus 25 plus 25, this become 550 mm. Just I am converting into meter, 0.5 meter, and this become 0.55 meter. So area of pipe is equal to pi by 4 minus d square minus d square. So pi by 4 0.55 bracket square minus 0.5 square is equal to, after these calculations you will get this answers of this area of pipe. Area pipe is known, so we can calculate the weight of pipe. Weight of pipe per meter length, per meter length. So weight means density, area of pipe into density, area of pipe into its length into density. So area of pipe 0.04123 meter per meter, that's why length is equal to 1 and density is given, and we need into Newton, that's why 9.81. So 2912.16 Newton. This is the weight of pipe. Similarly, we can calculate the weight of water. Weight of water is equal to, inside the area of that water means that is internal diameter, pi by 4 into d square into L into its density into 9.81. So pi by 4, inner diameter is 0.5 per meter length, so 1, density is given 1000 into 9.81. so this become in Newton. So weight of pipe is known, weight of water is known, so we can calculate the total weight is equal to weight of water plus weight of pipe. So put all these values, all values we already calculated. So we now in this case we have calculated the weight, and according to the Flexural formula, m upon I is equal to sigma upon y. In that case weight is known, so we can calculate the moment acting. It is a simply supported beam, so maximum moment act at its center, and that is the standard relations we have already seen, WL square by 8. So W means 4838.35, length is given 12 meter divided by 8, 87090.3 Newton meter. Okay, now moment of inertia, it is a hollow section, so for that hollow section moment of inertia pi by 64 capital D raised to 4 minus small d raised to 4. So pi by 64 capital D means 0.5 raised to 4 minus inner diameter 0.5 raised to 4. Here you will get the moment of inertia of that hollow section about the neutral axis, 10 raised to 3 meter raised to 4. And here in that case y means y is the distance from neutral axis to outer fiber, so that y is equal to 0.55 by 2. So this becomes 0.275 meter. In this case, put all that value here in the above formula. In this flexure formula, m is known, I we have already calculated, sigma we have to calculate, and y is also known. So sigma is equal to 16.82 Newton per meter square. So in that case, it is a symmetrical section. This section is symmetrical. So, and it is a simply supported beam. So compressive stress is act in the above the neutral axis. This side, compressive stress above the neutral axis and tensile stress below the neutral axis. So in that side, this is a tensile stress, but both the values should be same. So sigma c is equal to sigma t is equal to 16.82 Newton per meter square. If we join this in this way, this is the stress distribution diagram for this compressive stress and tensile stress.